And the next speaker is Aleksandr Trufanov, and he will tell us something about G-Lab.
Thank you. It's a pleasure to thank you organizers for organizing conference, and it's a pleasure to talk here. Okay, so I will talk today about affine Laumon spaces and admissible representations of Laumon head. Like just so what we are going to discuss. The goal of our work was to study different settlement bases in some giant head modules and to derive some character formulas from this. We'll go deeper in this topic further. Yeah, so there are a few different motivations for this equation, for this research. One of them is geometric representation theory. Another one is gauge theories with surface defect, that I guess most of you know much better than me. And there is also further interesting questions in integrable systems connected with this. So there will be big community of algebra that acts on basis, and very interesting. So it will be very interesting from integrable system point of view of integrable systems. Okay, so yeah. So let me start with geometric point of view. So there is a affine Laumon space that I denote by P. It is a modular space of some flags of torsion-free sheaves on some surface P1 on P1. But we will not use this definition, so we just say that there is a definition. Yeah, and there are like different approach to it. One of them maybe not quite known for audience is that it is like a fixed point set of cyclic group action on Giesecker. Another point of view that you can describe it just explicitly through chain circular.
Sorry, so by Giesecker modular space, you mean instanton modular space, the
Yeah,
application
yeah.
of the instanton modular space on P1 times P1.
Yeah, so Jordan Quiver with yeah. Yeah, so there is some. Yeah. So this is yeah. So indeed, Giesecker is instanton modular space, and Laumon is instanton modular space for gauge theory on surface on on P1 cross P1 with surface defect. So indeed. Yeah, but I don't know a lot about this. You can tell me more. So yeah, let's go further. Okay. So yeah. So what about this affine Laumon space? What is interesting for us are two things. First of all, there is torus that acts on it. It's quite big torus. C star and +2. And second of all, there is an action of SRN head on this torus, on cohomologies and homologies too, of equivalent homologies of P with respect to this torus. And this action is geometric, so we will get used to. So there is Hecke correspondence that I denote by EDI, and it's should pull back, push forward, as always. Yeah. So there is geometric definition. We will not use it explicitly, but there is. And what we're really interested in is sort of like applying at Yabot. So I mean there is basis of fixed points in equivariant homologies, and this is in fact the basis that we are interested in. So these fixed points on P, they, with respect to torus, they are enumerated by some data that we call affine Girfan settling pattern. So what it is? It is a bunch of numbers, of integer non-negative numbers, not written here, but they are non-negative. Yeah, and there are a few conditions for them. First of all, this bunch of numbers lies under diagonal, including diagonal, main diagonal. Second of all, we have they are decreasing when you go down, and they are periodic when you shift on n like, along the diagonal. So this is the second condition. And also it's in some sense finite. I mean that if you go down very low from diagonal, you have 0. That's it. So and what? Yeah, and I denote the set of all these fine different settling patterns by GT with hat. So this is what enumerates our points. And yeah, if you get used to Giesecker, you maybe would like to describe this a little bit in other terms, in terms of n tuples of Young diagrams. So here you can see them. So I mean, choose one column, and it will appear to be just Young diagram. And then so we have n Young diagrams like that, and then they start to reappear. I mean, we have periodicity. Okay, so yeah, so n tuples of Young diagrams are just in one-to-one correspondence to our GT patterns, so just weird way to encode them. For some reason we want. Okay, so what's next?
Sorry.
Yeah.
And these tuples are like nested in one
Sorry?
of the are nested the Young diagrams in the sense that one is a subdiagram of the other, or are just generic?
Sorry, I didn't get that.
So if the n tuple of a Young diagram is kind of Young diagrams which are nested one in the other,
No.
or
They're
are
just
arbitrary?
just arbitrary. So yeah. So it's like yeah. So it's just n Young diagrams, and now no conditions for them. So they're just n Young diagrams. You see, the arrows here are the inequalities, and there are no inequalities between neighbors. So and I forgot to say, yeah, maybe if you have seen Giesecker moduli space, you know that fixed points on it are enumerated by n tuples of Young diagrams. These are these diagrams.
Okay, no, because I know that in this GT pattern usually you also add these conditions.
Yeah, but these
inequalities.
conditions sort of yeah. I guess you have intuition from finite dimensional worlds, yeah. We will come back to this, but for now there are no conditions except this. So
Okay.
there are no conditions between two Young diagrams, and we will study interesting conditions that will appear. Yeah.
Thank you.
Thank you for the question. So yeah, so now, yeah, there is so as we've seen before, there is geometric action of homologies. So let's see how it looks like in basis. Yeah, so this is theorem of Feigen, Finkelberg, Nebert, and Rybnikov that there is an action by Chevalier generators, and you can write it explicitly with matrix elements rational functions. Some, yeah. And so what you should learn from this? If you act by EI generator, you just choose E's row, the row number I, and you try to decrease each number in this row to 1 when you act by EI. So here there is some sum and there is sign. This is what we really do. And matrix elements are some rational functions that depends on equivalent parameters, who now is xi, xj, and from the numbers that we have in the column, and also in row and in upper. It could also depend on numbers in upper row or in lower row, depending on. That's it. And so for lambda, so and okay, there is SLN head action, and we have such a, so we can consider linear. Yeah, so we consider linear span of all these points. It will become module, and this module. So yeah, so this action is defined as well defined for generic lambda. So I want to say that there is some parameter lambda that it's more or less the same parameter that x is the set of x, but we can pack it to SLN weight and to numbers that more or less like corresponds to JL. So I mean the difference between SL and JL is number u. Okay, so and in the end we have this module, and it appears that this module is just isomorphic to Verma JLN head module.
So, but you have some kind of deformation parameters in there. How do they enter the parameters of the Verma model? So the weights of the Verma model.
You ask what is H bar and H bar.
For example, yes.
Okay. H bar. Okay. So first of all, yeah, all this action is homogeneous by H bar. So I mean you can simultaneously. Okay, not by H bar, but simultaneously you can dilatate all equivalent parameters, and action will not change. Second of all, indeed there is H prime, H bar prime, and yeah, and if you look very carefully, you can see that in fact H bar prime to H, it is level plus m.
Okay.
So yeah, so H bar. So if you fix level for your affine Lie algebra, so how central charge acts, you fix the ratio of H bar prime to H. Yeah, it could be. Yeah. That's it. So there is this Verma module, and yeah, we are happy with this. This was done quite far. Yeah. So what we will study? We will study what happens if lambda is special. So what's the question we really have? And if lambda is special, then we have the following issue. Then in formulas of action, in our basis, we have some denominators start to vanish sometimes. So that's the problem. You see red terms, there are some difference of xi minus xj there, and for special values they become zeros, so there are no action on all set of all set of different settling patterns. And so this is like the issue to specialize, one of the issues, to specialize lambda to special value from another point of view. So, and from this point of view, what we want to do, and what is our work about, is how to choose these patterns by such way, so throughout part of patterns, and the remaining part will be our new module, and this module, and the action on this module will be well defined. So there are no poles anymore when throughout part of diagrams. Yeah? Do you have any questions? So if you want to think about this from geometric point of view, this question has some meaning. Yeah. So, and it is the following: when you specialize lambda to some generic lambda to some special lambda prime, it corresponds to restriction from equivalent cohomology of T to equivalent with respect to T to T prime with the smaller torus. Satisfy some conditions. And the issue why my previous formulas did not work anymore, from geometric point of view, is just issue that PT prime is not discrete anymore. So you have now more difficult structural fixed point sets. Yeah, so let's go a little bit deeper to this direction. So what about this fixed point set structure? So in fact, fixed point set would be decomposed in three parts. First part is isolated fixed points like before. Second part, so that's the first I called A. The second I call B, and it is just compact components with dimension greater than 0. And the third is non-compact, non-compact. So in general there are all three types. As you've seen for generic type, for generic lambda, we had only A. And what we are trying to figure out, what happens in some good cases. In fact, okay, so we always, for any specialization, we still have what is called Poincare maps. This map from equivalent homology to equivalent homology. If you, yeah, yeah, and this, since this map is very functorial and so on, and it's a good, it respects the action of Hecke correspondences. So image of phi is still module of SLN hat, and now so in terms of fixed point components, it's just cuts non-compact, and we have what remains are compact components. So A's compact components of dimension 0, so points, and compact components of higher dimension. Okay, so what, and we want in fact we want some base in image of in this infi. But okay, it will not always exist. And what we really want, so geometrically, existence of this basis means that in fact this B, so non-trivial compact components, is empty. So then we have basis of fixed components, fixed point of isolated fixed points and image of. Okay. So yeah,
sorry, can I say that? So instead of cohomology, you're going to consider homology. Can I view it as the dual representation of the GLN hat?
Yeah, that's a good point. Yeah. So
and it's somehow going to solve your problem, considering the dual representation, and then
Yeah, depending on what your problem is. So, I mean, yeah, you are right. In fact, this module homology is what is called contragradient dual Verma module, and this one is just Verma module. But what we are trying to study is Gelfand settlement bases in these modules. So yeah, this picture always exists. Yeah, but and what is true is that image of phi is just irreducible quotient of Verma module. So this is module map from contragradient from Verma to contragradient. It's unique, and image is just irreducible. Don't be if you don't like contragradient modules, don't be afraid. We will not use them. Yeah, but yeah. So the point is that sometimes in these irreducible presentations we still have a basis, and yeah. So where it happens. So we have very good case when it happens, and like more or less morally it seems like it's all cases, but we don't have such theorem. What we have is the following. So consider lambda. So I say that lambda is dominant if it pairs with any positive root for affine root system to non-negative numbers with shift on row. So on non-negative, so either on so yeah, so the condition lambda is dominant. It's a little bit more general than like integrability. So integrable case is one of the cases, for example, and another is when lambda is generic. So I mean, if all pairings are just complex numbers without not integers, then it's also dominant. So it's like some interpolation or extrapolation between Verma module and, for example, integrable module. Or if you
Sorry, AIs are non-negative integers.
yeah, it's in integrable case, AI are non-negative integers, and then it's still dominant, but it's just one of cases. Another case when all AIs, if you want just complex numbers, generic.
But I goes from 1 to n.
From or from 0 to n.
I see.
From to n minus 1. Yeah. So omega I, if you want to ask, omega I are fundamental weights for a certain hat. For a certain hat. Yeah. So yeah, that's a little bit technical definition, but yeah, but that's like that's the heart of what's happening. In fact, so I mean, this condition is really the condition where our technique works. So yeah, we need some just also technical definition what is how to parameterize positive roots in this case. So it's convenient just to say that we have alpha LR that are just sum of alpha A plus alpha L plus 1 and so on to alpha R minus 1. So yeah, so if you consider finite case, it will be just it's clear that they are all positive roots are like that. In infinite case, you should consider LR lying in integer numbers, and then it still will be true.
But what does it mean, alpha with L greater than n?
Yeah, then we cyclically we continue alpha periodically.
Okay.
So yeah, so for example, you can ask there is imaginary root delta, yeah, sometimes we call it delta, and it is just sum from alpha 0 to alpha n minus 1.
Okay.
So yeah, so luckily imaginary root is positive, so everything is good. Yeah. Yeah, so this is the way how we can represent this phi plus. And then, yeah, then this condition for dominant weights, you could rewrite it in terms of our equivalent parameters that we started from. We started with, and it is the following conditions that alpha LR pairing with lambda rho is, first of all, alpha LR pairing with lambda rho is just difference of XL minus XR divided on 1 h bar. I don't know, I remember you or not, I continued X by periodicity. So, yeah. And with this shift on H prime. So, in terms of affine algebra on some level. Yeah. And, yeah, and what I wanted to say. Here. I wanted also to say that so we can see the positive roots. And some of them pair to integers, some of them pair to complex numbers, we don't care, and some of them pair to integers, and we can call it integral roots or something, I don't know, and I denote it by phi plus lambda. So there is some subset of all positive roots that pairs with our lambda. For example, if in integrable case it's all there, this is just all positive roots. And in generic case, this is just zero. Nice. Yeah, and this is crucial. I mean, you asked me about where are the conditions for different columns, and they will appear soon. And for each alpha LR and phi plus lambda, we need a condition. So we will see. There we are. So yeah. So now I want to define what set of patterns we should choose. So if we choose lambda dominant, we should throw out part of diagrams, and we will define the module on this on remaining. And yeah. Definition is the following: so that we, if we have alpha LR positive root, then we should consider inequality. We should add inequality between DIL and DI plus 1R, but with some shift. I just, diagrammatically, I denote it like that. So I draw arrow, and I write a shift, just for simplicity. Yeah, so you see, now, like when we consider GT, we can consider lambda. If we consider dominant lambda, we have some inequalities like that, additional. We ask them to be satisfied. And also, what is important here? Here you can see why I like dominant weights in this moment. Because I want this inequality to be shifted on positive number, on a negative number. Why it is? Because otherwise, for example, zero pattern, where all are zeros, will not satisfy it. And so it will not make a lot of sense. So this dominant condition is quite natural from this point of view. We should consider such inequalities. Yeah. We will come back in a few minutes to the case of integrable, and the inequalities will be much simpler. Yeah, but in general, we have such inequalities. And so now I guess we are ready to the main theorem. So the main theorem is that if we consider the linear span of all given unsettling patterns satisfying these inequalities, so permitted. I call these patterns permitted patterns for lambda. Then they form a basis, so they form a representation of SLN hat. And moreover, this representation is isomorphic to irreducible quotient of Fermat module for J and H. So this is the main theorem.
Is there an analog of something like character formula for this, and can you refer
Yes,
this?
this will be, yeah.
Ah, okay.
Yeah. Yeah. There is. Indeed. Yes. Yeah. Yeah, so it's and here it is. So first of all, yeah, so if you would, yeah, so for these dominant weights, okay, almost for all of them, but I think there is some condition that there is in Katsukimoto papers that for me seems to be a little bit technical and not really useful, but somehow he used it, I don't know. Because like for our technique we don't need this condition, but they use it. So if they consider lambda that is dominant, but also satisfying some additional conditions that I ignored, then character of irreducible representation with such a weight will be summed by what I call integrable wire group. So this is wire group generated by integrable roots. So by roots that pair with lambda on integer number. Real roots. Yeah. So there is such a form. So you I don't know. When you look at this, I think you should in your heart you should see. Yeah, this is like Weil character formula for sure polynomials. And so this is like classical results. And so what we do, like we give, in terms of characters, what we have done, we found description of this character in other terms, in combinatorial. So you gave them combinatorial description. So you say that this character, in fact, is just generating function of these permitted patterns. So it's not very, like I would say, not very explicit, but depending on lambda, it could be more or less explicit. We will see the cases a little bit later. So yeah, as I already said, you should, if you love, as me, sure polynomials, you should compare it with this. So for sure polynomial, you have two formulas. One is Weil formula, where you have some denominator that corresponds to this B of M0 U, and you have sum by just ordinary Y group. And on the other side, you have formula through semi-standard Young tableau. That is, maybe you have heard, that semi-standard Young tableau is some reformulation of, by some reformulation you can say that this is Griffin-Zetlin patterns for finite case. So what we do is generalization of this. So this formula is the same as this, generalization of this, and the formula for generating function is generalization of generated function for semi-standard Young tableau. That's it. Okay. Questions? What next? So one special case, or I mean like dominant, maybe not that advertising, but there is like special case of dominance that maybe some of you could see at some moment. It's very useful for conformal field series, for study of double multiples and so on. They're called admissible representations. Yeah? So this is very special case of dominant, and for admissible, so for weight to be admissible, we need two things. One is to be still dominant, and another we want also that this integral roots, the set of integral roots generate whole Cartan. So we want phi lambda be of full rank. So yeah, it's not so obvious from this definition, but you can see it if you look very carefully. That level in this case is necessarily integer or is necessarily rational and has the following formats. It's shifted to dual Coxeter number, so to minus n.
So integrable representations are also admissible. They're a
Yes.
subset.
Yeah. So integrable as the simplest case. So it's so all admissible representations are enumerated by rational number by p and p prime. So like minimal models, you should have such association. And and integrable models correspond to the case when p prime is equal to 1. When you don't have denominator. So if you like integrable modules, we also consider them, but for integrable this result was no. We will discuss it a little bit later. So what happens in this case for admissible in this generality? It appears that so as you explained to you, our Giffen-Settling patterns are in one-to-one correspondence with n tuples of Young diagrams. So Young diagrams, and in this case, they are. We can rewrite the conditions, these permitted conditions, in a very simple way. We can say that in fact it's what is called Bursch conditions, and this is when you have n Young diagrams, and each of them, so they are like situated cyclically, and each of them is bigger of next one with some shift by both of axes, by ai from one direction and by bi into another direction. Yeah, so if you remember yesterday Thomas was talking about the beginning of his talk. He explained them. He showed us some pictures with plane partitions, minimal models. So this, what we are doing is colored analog process. Because like GLN, why colored? Because you have GLN weight, and so in fact, so there is color. So what next? Yeah, so let's. Yeah, so integrable case is the easiest one what you could consider, and then like I said, then we have inequalities between neighbors. So this inequality between d11 and d22 corresponds to root alpha 1 2. So it's in fact alpha 1 2 is just alpha 1, and it's one of the simple roots. So we just for each simple roots we have inequality. And this is, so we have such very simple picture. And and in this case, inequalities will be shifted just on numbers, right, written in coefficients near to fundamental weights. And that's it. And also, you can see that, okay, this are n Young diagrams, and you still can consider it like some partitions, plane partitions, more specifically by cylindric plane partitions. So this is the case. If you compare this previous slide, for example, This is the case when there are no BIs. Yeah, so there we are. Yeah, but yeah, so you have questions about this? So okay, so what we have to do to prove this? To make it zero. The idea is the following. So we had these formulas for matrix elements. You have seen they are quite big, not that big. You have seen bigger formulas. So okay, there are operators EI, FI that so they are between. They are matrix elements. We have matrix elements between all differentiated patterns. But what I want to say is that if we restrict this this matrix, if we consider only matrix elements between permitted patterns and something else, then it appears that there are no poles at all, never. So this is so the matrix elements from permitted patterns to any are well defined. But there are zeros. But if you consider for all, there will be poles. You have seen. Then the second part is that if you consider zeros, if you consider matrix elements between non-permitted pattern and permitted pattern, it appears that they are all zeros. Some not very hard statement, but requires some carefulness when you check it. And together, these statements, what they give? They in fact give you that you can restrict EIFI to permitted patterns, and moreover, they automatically give you quadratic relations. So if you try to check quadratic relations on EIFI, you will have it automatically from this to statements. But I don't know if you. But there are some problems. There are two problems that we should be careful. One is cell relations. Cell relations are of order 3, so this technique is not enough. So we have action that's like quadratic relations, but we don't know anything about cell relations for now. This is the first problem, and the second problem that I was tricking you a little before, it is that in fact I showed you only SLN head action, but SLN head is quite different from JLN head. So if you consider finite case without head, SLN and JLN, they are almost the same, like up to center. But here the difference is Heisenberg and, for example, like Fermat module or any other module, they are different to Fock space, tensor on Fock space. So it's quite serious difference. And so yeah, and we should somehow fix all these problems. And the secret how to fix it, in fact, is action of affine Yangian. So in fact, in the paper of Finkelberg, Negov, and Brimnikov, there was also action of Yangian, also geometric, on the same space. And it appears that if you compare this, so SLN head action was not irreducible. So the module was not irreducible as SLN head module. But as Yangian module, it appears to be reducible. So like, if you don't know what is Yangian, just very big algebra, current, so sort of like current deformation of current algebra of SLN heads. And then if this module appears to be reducible, I mean this one that Fagan FFNR had, and our module also is reducible. We can check it. It requires some work, but it's easy to check. And then automatically, if it's reducible, it has to satisfy cell relations. Otherwise, there will be some submodule generated by cell relations. Also, for this, it's useful that we have evaluation map, so called Guy evaluation map, from affine Yangian to universal helping of J-Allen hat. And in fact, this as Yangian modules, these modules L lambda U is just evaluation model, pullback of evaluation modules. That's it. So yeah, it was a little bit technical, but yeah, but we are not so far from that. So yeah, what else I can say about all this story? First of all, if you find J-Allen enjoyer, then you can have the same results from what we did by restricting on finite case. So it means that in our GT patterns we should fix zeroth row to be equal to 0. So all d0 dot we set to 0, and all periodic too. And then from this periodic infinite picture we will have just triangle that remains. And this will be Griffin settling pattern for Verma module for J-Allen, and then if you consider some specializations, you will have some quotients of Verma module, so you can also do bigger generalities than just for finite dimensional representations of J-Allen, but you can do it for any dominant representation of J-Allen. Yes, this result is not new for finite case. It was some work of Futorn and Carters. They did something similar. There is such results, but they used completely different techniques. The second thing that I can say about this, all this story you can repeat in a few cases. So in this case, affine Yangian that I used in previous slide, you should change to quantum toroidal algebra. Equivalent homology, you change to K-theory and so on. Yeah, and the other question the other stories that may be worth to mention, that on, I know if there are some enjoyers of crystals here, but for example, for finite case there is a natural crystal structure on GT patterns, and it appears to coincide with crystal structure corresponding to finite dimensional modules. And here we can easily reproduce the same. We can easily give the same definition, and there are some good properties of it. For example, we can see the number of highest weight vectors with respect to SRM hat will have size of Fock module. But there are some questions that were not very understood. If this crystal somehow connected with crystal of this representation or not. Yeah, so there we are, I guess. Conclusion and finish. So what we have done. So we constructed a Griffin settling basis for dominant reducible representations, in particular for admissible representations, we have seen from this generalization of formula for characters through as generating function of this partition. Yeah. But still there are some questions. First of all, the question is, do we have some, that already mentioned, that is crystal structure. If we have some crystal structure, the question is, what we can say about this crystal, if it's good in some sense. The other question is, can we somehow deform, so like, can you, if you have this differentiating patterns and story about differentiating basis, it always goes together with some integrable systems. And the question would be asked what we can say about them. Now I cannot say anything, but if you know something, if you have ideas, I will be happy to hear. And also, this differentiating basis, it's basis of, so in the same about beta algebras. Yeah. And other question is, if these cases are all cases when differentiating basis exist or not, I mean irreducible quotients of thermometers. And seems like that's all the cases, but we don't have such statement. But our I would say that our conjecture is that it's all, these are the all the cases. Okay, so thank you.
Thank you. Any questions?
Can you describe Whittaker vectors in your representations?
Yeah, Whittaker vectors, good question. In terms of geometric, from geometrical point of view, Whittaker vector is it is sum of units in cohomologies. Yeah, so so of course we can. Yeah, and I guess so. If we had formula for so and Whittaker vector exists in contragradient module Fermat. So we can just can restrict the formulas for Whittaker vector in to say. No, sorry. One second. I forgot. Does it exist in irreducible representation? So it exists in contragradient Fermat module, and the question is if it restricts to.
No, my understanding is that it's not necessary exists because we take vector a certain limit of conformal blocks where something goes to infinity, and this could have a difference like with fusion rules.
Mm-hmm.
What exists is actual conformal blocks.
Mm-hmm.
So not in this setting, but in setting of like Giesecke, when you want to compute like conformal block for minimal Virasoro modules. This can be done using similar prescriptions. So therefore, probably this prescription can be used to compute conformal block, for example, for integrable representations of the affine, affineness of the affine. Yeah.
But you see what I'm getting at. I want to take the norm of the Whittaker vector and then get this affine Laumon function like Shirashi like.
So with mass, you can take this function with masses.
Yeah. Okay. I take it with masses and
So
then
what joint mass can be?
maybe I send them somewhere or maybe I don't.
So the answer is that just to take a vector we cannot, but we can define these chains, generalized Whittaker's vectors, and for them we can do so. Yes, so we can try to calculate matrix elements for them. Yeah.
Okay, thank you.
Any other questions?
Yeah.
You mentioned surface defects. What would be the interpretation of this surface defect for this lambda, for instance? That you...
That's a good question, but I hope that someone audience can answer because I'm not that good in large series. So I can say that okay. So about surface, so I cannot answer this question.
But what was the question?
The question is what this result means from the point of view of surface defect and gauge series.
Gauge series.
Gauge series. My pronunciation.
And this-
Special parameters of the surface defect,
This
I guess. Like,
lambda. So this lambda is some kind of coupling, some parameter of the defect.
yeah.
It's some sort of resonance.
Yeah, some
between-
special values of the fluxes or something.
Okay. And what happens if it truncates the instanton sum in some way?
Yes.
Mm-hmm. Thank you.
Any other questions? If not, like, thank this. So we have a break.